Good morning, welcome back dear students. I am your physics professor Dr. Nagaraj explaining engineering physics for computer science and allied branches. So right now I am talking about superconductors. This is the third video on this topic. So in the previous video I was talking about Meissner effect and properties of superconductors. Come, let us proceed further. So whatever I teach today in this video, you can expect two questions. Both are equally important. Number one, distinguish between type 1 and type 2 superconductors, or classify the superconductors, or explain the classification of superconductors. That is one question. Another one, most important, explain the formation of Cooper pairs and give an account of BCS theory, or explain BCS theory, or explain the superconductivity using BCS theory. Both are equally important. You can expect them for 8 to 10 marks. Okay, first I start with types of superconductors. See, this type is totally based upon what is called critical field. In the previous video I was telling, see, the susceptibility is a negative in the case of superconductors, and when you plot magnetization versus magnetic field intensity, well, magnetization is a negative. What do you mean by negative magnetization? See, suppose if there is a specimen like this, inside if you have magnetic dipoles aligned in this particular direction, if you apply the magnetic field in the same direction, what happens? The dipoles will start orienting in the opposite direction. That means the direction will change. So dipole moment means magnetic dipole moment is opposite to the applied field. So total magnetic dipole moment is called magnetization, or called intensity of magnetization. In total, if this is the dipole direction, or if this is a magnetic dipole orientation, if I apply the magnetic field, immediately it will reverse. So dipoles are always orienting in the opposite direction. That is known as negative magnetization, and this happens in case of diamagnets. If you increase the external magnetic field, opposite orientation keeps on increasing. So negative magnetization keeps on increasing up to certain value. Afterwards it decreases and becomes zero. The point where negative magnetization vanishes is called critical field. Dear students, this is little bit confusing. What is the speciality of superconductor? Superconductors are not only having zero resistivity, they also have diamagnetic property, I said. So an exclusive property of diamagnets is nothing but negative magnetization. So superconductors, they will try to retain the negative magnetization. That means they will try to retain the diamagnetic property up to certain extent. So the dipoles will try to orient in the opposite direction till some extent. But at one stage, dipoles cannot fight against the external magnetic field. So they also start orienting in the same direction. The moment they start orienting in the same direction, what happens? It is nothing but paramagnet. So in paramagnet, dipoles are in the direction of the magnetic field. In diamagnet, they are in the opposite direction. So negative magnetization keeps on increasing. That means superconductor will try to retain its diamagnetic property, but beyond HC it cannot. It will surrender. So therefore I call this portion as superconducting part, this as normal conducting part. So this is very important graph. It is graph of negative magnetization versus critical field. So with the help of this graph, I am going to explain the type 1 and type 2 superconductors. So you need not have to explain this graph in the beginning itself. So you, when for example, if the question is distinguish between type 1 and type 2 superconductors, you can go ahead from here onwards. See, whatever I explained so far is actually type 1 superconductor. So please recall my previous two videos: critical temperature, isotopic effect, Meissner effect, critical field. All these things, whatever I explained, are for type 1 superconductors only. Well, then what is the type 2 superconductor? What is the difference between type 1 and type 2 superconductor? This question will come to your mind. So without much delay, I will give you the definition. See, if superconductor is having only one critical field, then it is called type 1 superconductor. If there are two critical fields, then it is called type 2 superconductor. Sir, is it possible to have two critical fields? Does it mean that superconductor superconductor will lose its property twice? No, it is not like that. There is a difference. I will explain it. First, I am giving only the definition. If there is only one critical field, it is type 1 superconductor. If there are two critical fields, it is called type 2 superconductor. See, type 1 superconductor is like this. For example, aluminium. Aluminium up to 0 Tesla, from 0 Tesla to, yesterday I told from 0 Tesla to 0.01 Tesla, it will be in superconducting form. If you apply the magnetic field beyond 0.01 Tesla, it will convert into normal conducting form. So aluminium is a type 1 superconductor. Well, in aluminium, if I take a piece of aluminium, if the applied field is less than critical field, then the magnetic lines will be going like this. This is what is known as Meissner effect. Lines cannot enter into the specimen. So type 1 superconductors exhibit perfect Meissner effect. Understood? Next, in type 1 superconductors, magnetic field, critical magnetic field is very, very small, 0.01 Tesla. Therefore, we also call them as soft superconductors. Soft is not that they are physically soft. Soft in terms of the magnetic field value. That means they cannot sustain huge magnetic field. They will surrender to a smaller value. Therefore, they are called as soft. Okay, they are soft by nature in terms of magnetic field. Hence, we cannot use them to store magnetic field. Dear students, this is one of the application of the superconductor. Superconductors ಅನ್ನು ಉಪಯೋಗಿಸಿಕೊಂಡು huge magnets ಅನ್ನು ಮಾಡಬಹುದು ನಾವು. We can use those magnets to lift the train. You might have heard of maglevs, magnetically elevated vehicle ಅಂತ ಟ್ರೈನ್ಗಳು ಜರ್ಮನಿ, ಜಪಾನ್, ಫ್ರಾನ್ಸ್ ಅಲ್ಲೆಲ್ಲ ಆಲ್ರೆಡಿ ಇದಾವೆ. ಸೊ ಇವು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಟ್ರೈನ್ಸ್ ಇವು. Whole train we can lift with the help of superconducting magnet. That I will try to explain in the application part. But anyway, for computer science branches, this maglev application is not mentioned in the syllabus. Okay, just only for the sake of additional information I will try to give at the end. Well, back to this. Right now I am talking only about type 1 superconductor. Type 1 superconductor is one in which there is only one critical field and the magnetization versus H is like this. There is only one critical field, and in type 1 superconductor there is a perfect Meissner effect. All the magnetic lines will be expelled below critical field, and because their magnetic HC critical field is very, very small, they are also called as soft superconductors. Because of that, they cannot be used for constructive purpose. They cannot be used to build huge magnets. Okay, so this is about type 1 superconductor. Now comes type 2. If I explain type 2, then you can make out the difference between type 1 and type 2. So now it is type 2 superconductor. So this is type 1, this is type 2. In type 2 superconductors, as I told in the beginning, there are two critical fields. The graph of -m versus h is like this. As magnetic field increases, this negative magnetization also increases, but it won't increase further. It starts decreasing, but it won't decrease suddenly. If it decreases suddenly, then it is type 1 only. The decreasing tendency starts here. Decreasing tendency starts here, continues to decrease, and after a huge value of h, a very large value of h, that negative magnetization becomes zero. So the point where the decreasing tendency starts is called as critical field number 1. The point where it finally vanishes is called critical number 2, critical field value 2. So this way there are two critical fields in the case of type 2 superconductors. So now you got the answer. That means superconducting property is not vanished once for all. Like in superconductor 1, type 1 ನಲ್ಲಿ ವ್ಯಾನಿಶ್ ಆದಂಗೆ ಅಬ್ರಪ್ಟ್ ಆಗಿ ವ್ಯಾನಿಶ್ ಆಗಲ್ಲ ಇಲ್ಲಿ. ಇಟ್ ಈಸ್ ಎ ಗ್ರಾಜುಯಲ್ ವ್ಯಾನಿಶಿಂಗ್. ಸೊ ಇನ್ ಟೈಪ್ 2 superconductor, decrease in the tendency starts, decreasing tendency starts at HC1, and then finally it becomes a 0 at a very large value. Hc2 is very much greater than Hc1. Hc1 is about 0.0102 like that. Hc2 is very, very high. For example, we have niobium tin having Hc2 value around 24.5 Tesla. Look at 24.5 Tesla, whereas this one is 0.01 Tesla. So compared to 0.01, this is more than 2000 times. Okay, 2000 times more. Similarly, in case of niobium and titanium, it is around 15.6 Tesla. So in case of type 2 superconductors, Hc2 value is very high. Because Hc2 value is very high, we call them as hard superconductors. Got it? And because they are able to hold huge magnetic field, we can use them to build permanent magnets, right? So type 1 cannot be used to construct permanent magnets, whereas type 2 can be used to construct permanent magnets. And from 0 to Hc1, it is perfect superconductor. Above Hc2, it is perfect normal conductor. What about between Hc1 and Hc2? Dear students, follow carefully. From 0 to Hc1, type 1, type 2 both are same. From 0 to Hc1, type 1 and type 2 both are same. Their behaviors are same. Beyond Hc2 also they both are same. Okay, only from Hc1 to Hc2 this portion is there, no? This is the speciality of type 2. Well, from 0 to Hc1 it is perfect superconductor. From Hc2 onwards it is perfect normal conductor. What about from Hc1 to Hc2? Follow carefully. It will be in the mixture. It is in the mixed state. It is partially superconducting, partially normal conducting. That means it is both superconductor as well as normal conductor. What actually it is, I will explain now. Before that, I repeat, from 0 to Hc1, that is from here to here, type 1 and type 2 both are same only in behavior wise. Similarly, Hc2 onwards also, type 1 is also normal conductor, type 2 is also normal conductor. Only difference between Hc1 and Hc2, type 2 behaves slightly in a different manner. What is that different manner? It is actually called mixed state. Now I will explain what actually happens here. For that, let me take a superconducting slab. Instead of circular disc, I take a slab now. Okay, this is one rectangular slab of superconductor. Now do one thing, apply the magnetic field. When you apply the magnetic field initially, yes, definitely they will be thrown out. So Meissner effect is happening. Okay, but if you go above Hc1, what happens, you know? Some lines will try to enter the superconductor, not over the entire region. See, for example, this line is thrown out. Okay, this line may enter. This line is thrown out. This line may enter. So, magnetic lines slowly get into the specimen. This is my specimen. That means between Hc1 and Hc2, Meissner effect is not perfectly happening. So therefore we can say type 1 superconductor, perfect Meissner effect they exhibit, whereas in type 2 there is no perfect Meissner effect. When the field is greater than Hc1, these magnetic lines slowly they start entering. Once they start entering, at least that portion is no more a diamagnetic portion. If it is not a diamagnetic portion, we cannot call it as a as perfect superconductor. But in this region, it is a diamagnet only. And whether magnetic lines enter or don't enter, still resistivity is zero. Nodi, nanu indina video dalli helidini, in order to call a material a superconductor, two important properties we have to look for. Number one, diamagnetic nature. Number two, zero resistivity. Here what is happening when H is greater than Hc1 in case of type 2? Magnetic lines are managing to enter into the specimen. If not over the entire surface, at least in smaller regions, we call them as filaments. ದಾರದ ತರ ತೂರ್ಕೊಂಡು ಹೋಗ್ತವೆ. They try to penetrate through the specimen. That way, the diamagnetic property is disturbed, but still superconductor is able to retain its zero resistance property. So, in terms of resistance, it is superconductor. In terms of diamagnetic nature, it is not superconductor. That is why I called it as mixed state. Okay, so between Hc, when H is greater than Hc1, this is going to happen. You keep on increasing this, then some lines here also will start enter, here also will start enter, here also will start enter, and finally a stage will come when H is equal to Hc2, all the lines will enter in. Now the zero resistivity also vanishes. Now it converts into normal conductor. So from 0 to Hc1, perfect superconductor, type 1 tarane. From Hc1 to Hc2, mixture, diamagnetic property vanishes, zero resistivity still exists. Hc2 onwards, diamagnetic property also vanishes, zero resistivity also vanishes. So this is about type 1 and type 2 superconductors. Well, now let me summarize. This is a very important question. You can identify about 6 to 7 differences. Number 1, type 1 they have only one critical field, type 2 they have two critical fields. Type 1 ಅಲ್ಲಿ Hc1 is very small, Hc2 very high, about 1000 to 10,000 times high in some cases. And type 1, because critical field is very small, they are called as soft superconductors. Type 2 are called hard superconductors. Type 1 exhibit perfect Meissner effect, type 2 do not exhibit perfect Meissner effect. Type 1 exists only in two states, namely superconducting and normal conducting, whereas type 2 exists in three case states, superconducting, mixture as well as normal conducting. So in case of mixed state, it is partially superconductor because zero resistance exists but diamagnetic nature does not exist. Okay, so this graph also can be taken as one difference, minus m versus h is as follows. So that's all about type 1 and type 2. Dear students, you better give examples also. So I have given the niobium, strontium, niobium and tin, and niobium and titanium with the corresponding Hc2 values, and aluminium corresponding Hc1 value, that is 0.01 Tesla. So well, that's all about type 1 and type 2 superconductors. So please follow this carefully. This is one of the expected question for the main exam. Okay, well, with this now I move on to what is called BCS theory. Okay, now it is BCS theory. BCS theory stands for Bardeen, Cooper and Schiffer. B for Bardeen, C for Cooper, S for Schiffer. These three physicists gave this theory, and in fact for this theory they got even Nobel Prize also. Okay, Kemmerling-Onnes got the Nobel Prize, Meissner effect, Meissner got the Nobel Prize, even BCS, these three physicists also got the Nobel Prize. I told you already about 3 to 4 Nobel Prizes are awarded in the field of superconductivity. Well, what is this BCS theory? How it is going to explain superconducting property? Dear students, I tell you, this theory, explanation of this theory is not that simple. It is not possible to explain without any equations, and that too higher level mathematics is required, higher level quantum mechanics knowledge is required, but I will try my level best to make it as simple as possible, as understandable as possible for your level, at your level, and whatever the physics you know, I make use of only that much to explain this Cooper pair formation and BCS theory. Okay, so I just mentioned Cooper pair. What is Cooper pair? Cooper pair, see, very first sentence itself is very confusing. What is that? Cooper pair. What is Cooper pair? Cooper pair is a combination of two electrons. Cooper pair is a pair of two electrons. Okay, what is confusing here? It is pair of two electrons. Wait. Next part. How Cooper pair is formed? Cooper pairs are formed when two electrons attract attract each other. Don't you find something fishy here? Yes sir. Our PU teacher, our high school teacher told two electrons never attract. Yes, I am also telling the same thing. Two electrons never attract because they are negatively charged particles. Like charges repel, unlike charges attract. Similarly, like poles repel, unlike poles attract. But I am still going ahead with the same sentence. When one electron is attracted by another electron, they form a bonding between them. This overall combination is called Cooper pair. What is this, sir? You are telling it is not possible to attract two electrons. At the same time, you are telling it is possible to make the pair out of attraction. How do you account for this? Well, I will try my level best to explain how it is possible to make two electrons stay together. I am not telling that electrons are getting attracted. It appears to be attracted. My final intention is to make two electrons to stay together. When they stay together, when they move together, when they go look it together, it appears as if they are bonded together. It appears as if they are attracted together. So that situation is arising in case of superconductor. How it arises, what condition required, and okay, if Cooper pair is formed, how it is able to explain the zero resistivity and other things. Let us try to understand. Now try to follow this example. I take two bar magnets. This is one bar magnet, this is another bar magnet. Assume that this is north pole, this is north pole. When I bring them very close to each other, what will happen? Sir, it is obvious they repel. Yes, they repel. North, north, repel. Okay, I bring south, south. What happens? Same thing will happen, sir. North, north, south, south. They are like poles, they repel. Okay, now what will happen? Yes, you are correct. They will attract and they stick together. Right. So that means they are forming the pair. There is no wonder in this. It is the nature law. This is the law of nature. Unlike poles attract, like poles repel. But I want to break this. I want to attract. I want to join them together. How to do that? I want this south pole and north pole and north pole stay together and move together like this. Okay, how to do that? Can we do it? Is it possible? Can you think of a sort of correlated motion? This is called correlated motion. When this is going up, this also should go up. This also should go up. Both of them come down. When they are going right side, they should both right side, both left side like that. This is called correlated motion. Understanding, mutual understanding, well understanding between them. How to do that? Yes, there is a possibility. Now do one thing. Take a sheet of iron. Take a sheet of iron. Now bring this magnet's north pole here. What happened? Sir, iron sheet gets stuck to the magnet. Yes, you are correct. Iron sheet gets stuck to the magnet like this. Wait. Okay, so this is iron sheet, this is iron sheet, and when I bring the iron sheet very close to the bar magnet, the north pole gets stuck to it. So now it is this way. Okay, so it is like this, right? So iron sheet is now attached to my bar magnet's north pole. Next what I will do, keeping this here, I bring another magnet's north pole this side. When I bring another magnet this side, what will happen? That also gets stuck to the sheet, right? So here this side is getting stuck to the sheet not because that is north pole. It is not at all feeling north pole. It is feeling the iron. Are you getting my point? So I have a sheet of iron over here. From this side I bring north pole of the bar magnet. From this side also I bring north pole of the magnet. They both will get stuck to the iron sheet. Not from the same side but from the opposite side. Okay, so like this. Now if I move this one, this also will move. If I move that one, this also will move. That is possible only if the sheet, this paper I am treating as iron sheet. So if the sheet is cooperating, then both the ends will move together. So I can bring about what is called that correlated motion. Did you understand? So that means I am trying to establish a sort of attraction. I am trying to bring them together. I am trying to keep them together with the help of iron sheet. Without mediator. This fellow is a mediator. Iron sheet is the mediator. ಈ mediator ಇಲ್ಲ ಅಂತಂದ್ರೆ ಇವೆರಡು ಹಿಂಗೆ ನಿಲ್ಲೋದೇ ಇಲ್ಲ. They won't stay like this at all. I need this mediator's help. Without mediator, they fly apart. With mediator, they will try to stay together. This is in the case of bar magnet, in the case of magnetic field. So attraction between two like poles. Still it is not attraction. I managed to keep the two poles intact. Okay, now coming to electron. See, already in one of my video I mentioned, in the material we have what is called lattice plane. In the lattice plane we have what is called positive charge. Let us say positive charges are sitting at the corners of the lattice plane. Okay, now assume that one electron is moving towards the lattice plane. So this is my lattice plane, this is my lattice plane, positive, 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 positive. One electron is moving towards the lattice plane. What will happen? Because of the electron's negative charge, as it comes here, this positive will move little bit, this positive will move little bit, this positive will move little bit, this also will move little bit. That means there is a sort of attraction. Say this is my lattice plane, right? This is one positive charge. When electron arrives here, electron is negative, this is positive, so there is attraction, so this positive will come here. Similarly, this positive will come here, this positive will come here, this positive will come here. Yes, I know already some questions are raised in your mind. Sir, why positive is coming here? Why electron is not going that side? I have answer for that. Wait just for another 1 or 2 minutes. So time being, you just take it for granted that only positive are moving. Now the lattice, the positive charge is distributed. I am not telling that lattice size is shrinking. Lattice size ಚಿಕ್ಕದಾಗೋದಿಲ್ಲ. ಅಲ್ಲಿದ್ದಂಥ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ನೋಡಿ, ಇಲ್ಲಿದ್ದಂಥ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಇಲ್ಲಿಗೆ ಬರ್ತಾ ಇದೆ. ದಿಸ್ ಈಸ್ ಕಮಿಂಗ್ ಹಿಯರ್, ದಿಸ್ ಈಸ್ ಗೋಯಿಂಗ್ ಹಿಯರ್, ದಿಸ್ ಈಸ್ ಗೋಯಿಂಗ್ ಹಿಯರ್. ಸೊ ಆಸ್ ಎ ರಿಸಲ್ಟ್, earlier the charge was distributed over this much area. Now the charge is distributed over this much area. Come on, tell me whether charge increased? No. Whether charge density increased? Yes. How? What is charge density? Charge density is nothing but Q divided by surface area. Earlier this was the surface area. Now this is the surface area. Surface area decreases, charge density increases. So what I mean to say, when electron move towards the lattice, it will pull all the positive charges. This is called polarization of the charges. As a result, charge density increases. What type of charge density? Positive charge density increases. Okay, so I am not at all telling that positive charge is increasing. ಆಗೋದೇ ಇಲ್ಲ, charges ಅಷ್ಟೇ ಇರುತ್ತೆ. 4 charges only will be there. Charge density will increase. Got it? Okay, so all the charges are now polarized, crowded. As a result, charge density increases. Okay, then electron is here. Meanwhile, okay, now my electron is here and there is a lot of positive charge density in this region, lot of positive charge density. Now meanwhile, another electron coming from this side, another electron coming from this side will see the positive cloud. So ಈಗ ಈ ಕಡೆಯಿಂದ ಒಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಹೋಗ್ತಾ ಇದೆ ಅಂದ್ಕೊಳ್ಳಿ, it will see the positive charge cloud. So what happens? This electron also gets attracted by the cloud. So from that side electron is coming, from this side electron is going. This electron created the positive cloud here, and because of that this electron will stop here. Already this electron has stopped here, this also will stop here, and this electron will lose energy to the lattice, this electron will lose energy to the lattice. So as a result, there arises a sort of bonding between the electrons, but without the help of lattice it is not possible. Here the lattice is the mediator. Lattice must cooperate, lattice positive ions must cooperate, they must be flexible, they must be able to move towards electron. You ask the question, no, why positive charge is moving, why not electron? In a material, if positive charge is not flexible, if the lattice is not flexible, if the lattice vibrations are not too much, certainly Cooper pair will not be formed. ಅಂದ್ರೆ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಆ ಕಡೆ ಹೋಗಂಗಿರಬೇಕು, ಎಲೆಕ್ಟ್ರಾನೇ ಹೋಗಂಗಿರಬಾರ್ದು. ಅಂಥ ಮೆಟೀರಿಯಲ್ ಇದ್ರೆ ಮಾತ್ರ ಇದು ಆಗುತ್ತೆ. ಓಕೆ, ಓನ್ಲಿ ಇಫ್ ಇನ್ ಅ ಮೆಟೀರಿಯಲ್ ಲ್ಯಾಟಿಸ್ ವೈಬ್ರೇಷನ್ಸ್ ಆರ್ ಲಾರ್ಜ್, lattice is cooperating, then positive charges will move towards each other. As a result, cloud increases, electron stays there, another electron also will stay there. Now because of the attraction, electron will lose energy. I hope you following now. I repeat once again what is happening. I repeat in brief once again. When electron is coming this side, it will pull all the positive charges. As a result, positive cloud increases, density increases, so electron will stop there. From the other side, when another electron is coming, it will also stop there. So both the electrons will give their energy to the lattice. That's why this lattice is vibrating. Come on, tell me, lattice vibration is associated with what type of particle? In my first video I have mentioned, yes sir, it is nothing but phonon. Yeah, that is the reason why I explained phonon concept in detail in my first video. ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, electron lattice ಹತ್ರ ಬಂದಾಗ, when two electrons arrive at the lattice, they give their energy in a discrete manner. Each time they give some definite amount of energy in terms of particle, that is called phonon. So you can say, idu whatever I explained, this is for understanding. See, my teaching is like this. First I will try to explain the concept so that you can understand. Now you can put it in your own words. So concept ಅನ್ನು ಅರ್ಥ ಮಾಡಿಸೋದು ನನ್ನ ಟೀಚಿಂಗ್. ಆನ್ಸರ್ ಅನ್ನು ನೀವೇ ಬರೀಬೇಕು. ಯಾವ ತರ? ಸಿ, ವಾಟ್ ಈಸ್ ದ ಆನ್ಸರ್? ಹೌ ಕೂಪರ್ ಪೇರ್ಸ್ ಆರ್ ಫಾರ್ಮ್ಡ್? ಹೌ ಕೂಪರ್ ಪೇರ್ಸ್ ಆರ್ ಫಾರ್ಮ್ಡ್? Yeah, like this. When electron moves near the lattice, it will attract all the positive charges. As a result, charge density increases and electron will lose its energy to the lattice. Meanwhile, another electron moving in the opposite direction, it will also get attracted by the lattice and loses the energy. Both the electrons, because they are losing energy, they stay together, and the energy lost by them is in a discrete manner, that is called phonon. So when two electrons lose their energy, they stay together. Okay, always remember, when there is attraction, energy is less. When there is repulsion, energy is more. This is what you studied even in electrostatics also. Higher potential energy means repulsion, lower potential energy ಅಥವಾ negative potential energy means attraction. Okay, ಇಲ್ಲೂ ಕೂಡ ಅದೇ ಆಗೋದು. ಎರಡು ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಬಂತು, ಲ್ಯಾಟಿಸ್ಗೆ ಎನರ್ಜಿಯನ್ನು ಕೊಟ್ಬಿಟ್ಟು ಅವು ಅಲ್ಲೇ ನಿಂತ್ಕೊಂಡಿದ್ದಾವೆ. They are staying there. So this is now called Cooper pair. This is what I mentioned. So between these two we have what is called lattice plane. In lattice plane, positive ions should vibrate. If they refuse to vibrate, if the lattice plane does not cooperate, if it won't cooperate, Cooper pair will not be formed at all. When the Cooper pair is not formed, there will be no superconducting property. Okay, see, this is the reason why you cannot convert copper into superconductor, iron into superconductor. Even though iron and copper are very good conductors, they never become superconductors because the lattice is not vibrating. Lattice is very rigid. For us, lattice must be flexible. ಈ ಆಟಮ್ಸ್ ಎಲ್ಲ ಹತ್ರ ಬರೋಂಗಿರಬೇಕು. ಅಲ್ಲಿ ಕಾಪರ್ ಅಲ್ಲಿ, ಐರನ್ ಅಲ್ಲಿ, ಲ್ಯಾಟಿಸ್ ಅಲ್ಲಿರೋ ಪಾಯಿಂಟ್ಗಳು ಬಹಳ ರಿಜಿಡ್ ಆಗಿರ್ತವೆ. ಎಲೆಕ್ಟ್ರಾನ್ ಬಂದರೂ ಕೂಡ ಅವು ಹತ್ರಕ್ಕೆ ಹೋಗೋದಿಲ್ಲ. ಸೊ therefore they never become superconductors. Okay, coming back to this Cooper pair. So now you know what is Cooper pair. It is a combination of two electrons. How it is formed? With the help of lattice plane. What actually happens? When electron arrives here, all the positive charges will be crowded, density increases, so electrons get attracted, and therefore there arises a sort of virtual bonding between them. Okay, and this is a low temperature phenomena. In order to break this bonding, we have to supply some energy, that is called energy gap. It is possible to prove that it is 3.5 kB into Tc, where kB stands for Boltzmann constant, Tc is critical temperature. Okay, so Tc, if you substitute, it comes out to be, for like aluminum you substitute like 1.15, mercury you substitute like 4.15, calculate energy gap. So it is a very small value. That means Cooper pairs exist only at lower temperature. So why this is not happening in case of higher temperature? ಬೇರೆ ನಾರ್ಮಲ್ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ ಯಾಕೆ ಇದು ಆಗೋದಿಲ್ಲ? ನಾರ್ಮಲ್ ಟೆಂಪರೇಚರಲ್ಲೂ ಎಲೆಕ್ಟ್ರಾನ್ ಬರುತ್ತೆ, pulls the positive charges, but thermal energy will push the electron forward, it cannot stay there. So that is the reason why at normal temperature or higher temperatures electrons cannot form their pair. Okay, so this is one point regarding the Cooper pair. Second thing, this is also quite important. Once one Cooper pair is formed, okay, within no time all other electrons will follow the same procedure. Within no time, within a fraction of second, their number increases like anything. Okay, over 10 power minus 6 meter of length within the specimen, you will find billions of Cooper pairs, and all the Cooper pairs are identical. All the Cooper pairs are exactly same, and if one Cooper pair is moving like this, all other Cooper pairs also will move in the same direction. This is called correlated motion. So between each and every Cooper pair there is a mutual understanding. Whether it is a Cooper pair in the front row or in the back row, they all have mutual understanding. You might have seen birds flying in the sky. So the front bird will be like this, next we have like this. Have you seen? They have a beautiful arrangement, and they make this arrangement within no time. Suppose if the first bird deviates, they all will deviate and they all will move in the same direction. So this type of movement is known as correlated motion. Okay, so I just tried to explain what is Cooper pair, how it is formed, what is the speciality of the Cooper pair. Cooper pair no ವಿಶೇಷತೆ ಏನು, extraordinary property ಏನಪ್ಪಾ ಅಂದ್ರೆ correlated motion. Another speciality ಏನಪ್ಪಾ ಅಂದ್ರೆ ನೋಡಿ, ಕ್ವಾಂಟಮ್ ಮೆಕ್ಯಾನಿಕ್ಸ್ ಅಲ್ಲಿ ನಾವು ಪಾರ್ಟಿಕಲ್ ಅಂತ ಟ್ರೀಟ್ ಮಾಡಲ್ಲ. We never treat particle as a particle, we treat particle as a wave, and each wave is represented by what is called wave function. So one electron, one wave function. If there are two electrons, two different wave functions. If there are n electrons, n different wave functions. But here, even though there are n number of Cooper pairs, they all are represented by one wave function. That means all the Cooper pairs are behaving like single molecule, single particle. That is why we call that bunch of Cooper pair as macromolecule. ಎಲ್ಲದಕ್ಕೂ ಇಲ್ಲೇನೆ ನಿಮಗೆ ಸ್ವಲ್ಪ ಕಷ್ಟ ಅನ್ಸೋದು. ಈ ವೇವ್ ಮತ್ತು ಪಾರ್ಟಿಕಲ್ ನೇಚರ್ ಬಂದಾಗ ಸ್ವಲ್ಪ ಕನ್ಫ್ಯೂಸ್ ಆಗುತ್ತೆ. ಈ ವೇವ್ ನೇಚರ್ ಅಂತ ತಕ್ಷಣ ನಮ್ಮ ಮೈಂಡ್ ಬೇರೆ ಕಡೆ ಎಲ್ಲೋ ಹೊರಟೋಗ್ಬಿಡುತ್ತೆ. ಪ್ಲೀಸ್ ರಿಮೆಂಬರ್, ಇನ್ ಕ್ವಾಂಟಮ್ ವರ್ಲ್ಡ್, ಇನ್ ಸಬ್ ಅಟಾಮಿಕ್ ವರ್ಲ್ಡ್, ಪಾರ್ಟಿಕಲ್ಸ್ ಆರ್ ಕನ್ಸಿಡರ್ಡ್ ಆಸ್ ವೇವ್ಸ್. ಒನ್ ವೇವ್ ಮೀನ್ಸ್ ಒನ್ ಪಾರ್ಟಿಕಲ್. ಇಫ್ ಆಲ್ ದ ಪಾರ್ಟಿಕಲ್ಸ್ have same type of wave, then we call it as one wave function. So Cooper pairs are described by one single wave function. That is why Cooper pairs are called macromolecules. Okay, so I explained how Cooper pair is formed, what is the speciality of the Cooper pair, that is correlated motion, and why it is represented by one single wave function. Now the question is, okay sir, your intention is to explain superconducting property, that means zero resisting property and diamagnetic property. How Cooper pair is able to account for those two specialities? Superconductor ಅಂದ್ರೆ ಎರಡು ಸ್ಪೆಷಲ್ ಪ್ರಾಪರ್ಟಿ, ಎರಡು ಇಂಪಾರ್ಟೆಂಟ್ ಪ್ರಾಪರ್ಟಿ ಅಂತ ಹೇಳಿದ್ದೀನಿ. Two important properties, zero resistivity and diamagnetic property. Well, I will explain how Cooper pair can explain the zero resistance state of the substance and diamagnetic nature of the material. That I take up in my next video. So today in this video I just gave you the classification and the Cooper pair formation. So Cooper pair formation is one of the beautiful concept, very difficult to accept. Attraction between two electrons, our mind will not my conscious will not permit at all, but still it is true. It is true only when temperature is very, very, very small. Okay, well, I stop this video. Please like my video, share the video, subscribe to my channel and support me. Thank you very much.